Hey everyone, I am Marco and welcome to this lesson on anomaly detection in time series. This time I couldn't find any meme for this, very hard to find a meme for anomaly detection. Anyway, today what are we going to talk about? First, we'll talk about the different types of anomaly detection tasks in time series, and then we'll take a look at 3 different methods that you can detect outliers in your time series data. So we'll take a look at the mean absolute deviation that we will use to compute a more robust z-score. Then we'll take a look at the isolation forest algorithm, and finally the local outlier factor. Now, as always, you know what I like to do. I like to talk about theory first and then implement everything in code. So we'll be going back and forth between the slides and the notebook. And in the description, you'll have everything that you need. So you'll have the data set as well as the full source code for this lesson so that you can follow along. So let's get started. What is anomaly detection? Well, anomaly detection is a task where you identify rare events that deviate significantly from the majority of the data. And it's very useful, right? It's used in a wide range of real-life applications, from manufacturing to healthcare. And now, why would you do anomaly detection at all? Well, for 2 reasons. First, unexpected events usually are caused by some kind of production faults or system defects, right? And it's very important to identify those. So, for example, imagine that you're working at Amazon, right? And you're monitoring the number of visitors to the website. Well, if at any point the number of visitors falls to 0, clearly something is wrong, right? Maybe your website is down, and so you need to identify that as fast as possible so that you can fix it, okay? This is a pretty extreme example, but you understand, why we would do anomaly detection. And the second reason is that outliers can actually affect the performance of your forecasting models. So we know that in time series, any forecasting model uses past values to then predict the future, right? So if in your past you have some kind of outliers, well, you need to first identify them and then think, do you want those outliers to remain in your historical data to train your model on, right? Is it reasonable to keep them? Should you remove them or try to normalize, their values to bring it back, to more normal behavior in a sense, so that your forecasting model is more stable in the future, okay? So this is really the 2 main reasons why you would do anomaly detection. And now, like I said, there are 2 types of anomaly detection tasks that you can do with time series data. The first one is point-wise anomaly detection, and the second one is pattern-wise anomaly detection. And they're pretty self-explanatory. So point-wise, as it says, you are looking at isolated points in time that are outliers. So here you can see an example. This is actually the scenario we'll be working with in this lesson. It is the CPU usage of an AWS EC2 instance. So as you can see, those 2 red dots in the time series, there are 2 isolated anomalies that were labeled. And so we are interested in identifying them, okay? And then for pattern-wise anomaly detection, well, here you are looking to identify a sequence of points that form an anomalous pattern, okay? So here again in our data, we have another scenario here where we are monitoring the cost per click of an ad. And now you can see that the series of red dots is considered to be abnormal, okay? And so you would use other algorithms to identify this entire sequence of anomalous points. But like I said, for this lesson in particular, we will only focus on point-wise anomaly detection. So this is the previous example, right? We'll try to find, can we devise, algorithms that are able to identify these 2 red dots here. Perfect. So that's it for this little introduction. So before we actually move on to the first method, let me go back into the code, right? We'll read the data, import it, visualize it a little bit, and then we'll come back to the slides and learn about our first method. All right, and we are in the Jupyter notebook. Note that you can get this exact same code in the description. I will leave you a link to the GitHub repo. And for now, we are just going to import our data, read it, and visualize it a little bit. And of course, I am not writing the entire code from scratch because some parts are very boring, like library imports or plotting. I really want to focus on the anomaly detection techniques. So let's go ahead and run these first 2 cells. So again, I'm just importing the normal libraries that we use in data science, pandas, numpy, matplotlib, and then I am setting the size of my figures. Now here, this is where you can download the data set, so you can use the exact same data as I am, so that you can reproduce all the results. So anyway, a bit of information on the data. It's real life data on the CPU utilization of an EC2 instance in the AWS cloud. Data is recorded every 5 minutes starting on February 14th at 2:30 p.m. There's a total of 4,032 data points, and it's made available through the Anomaly benchmark, which is very cool repository. You have a lot of data sets with anomalies and the labels as well, and you can do either point-wise or pattern-wise anomaly detection. It's really cool, really grateful to have found this little repo there. So make sure to check it out and try things with different data sets after this video. So let's go ahead and read the data. So again, this is the data that I downloaded from the link that you can find here. And then once this is done, we're also going to take the labels. So the labels, this is the second link that you can see here. So basically here in our data set, we only have 2 points that are anomalies in this case. So before we move on, as you can see here on the timestamp, we don't have an actual timestamp type, right? Because of those slashes. So let's actually convert those dates to timestamp. So I will say that df timestamp is equal to pd.to date time, and then pass in again the timestamp column. Perfect. And now we have the right format. So this is great. We can actually move on. And now what I'm going to do is add an anomaly label. So, we are trying to do anomaly detection. So of course we need to find a way, is our method correctly identifying the anomalies or not? And for that we need a label. So df is anomaly. So this is a new column that I am creating, is going to be equal to 1. So by default, 1 here in this case will mean inlier, so not an anomaly. -1 will be an anomaly. This is basically the standard that scikit-learn is using as well. So all the models, a normal point will be 1 and an outlier will be -1. So we are using the same thing here, just to keep everything easy later on when we start modeling. So for each in anomalies timestamp, so now I'm going to identify my anomalies. I will say that df lock, and then here df timestamp, where it is equal to each. Then you will say that is anomaly is going to be equal to -1. Perfect. Once this is done, we can go ahead and display the head. So now, as you can see, we have our timestamp, we have the value, and now we have this label in the is anomaly column telling us if the point is an inlier or an outlier. And now let's quickly visualize our data. So here I'm just separating my anomaly and inlier data. And then I am making a plot, very standard plotting code here. And you should get the following. So let me zoom out a little bit so you can see everything. Perfect. So now as you can see, we have our data. So in blue, this is all the normal points, so the inliers, and in red, the outliers. So as expected, right? Just like we have seen in the slides, the 2 red dots are anomalies, and those are the points that we are trying to find out. Now, of course, keep in mind, right, because it is anomaly detection, we are detecting very rare events, which is why we only have 2 points here, right? So it's going to be very hard for our model, to find those points. And also when we evaluate it, it's really like either you hit or miss, right? So either you find these 1 or 2 points, or you completely miss them, right? So it's going to be pretty interesting, pretty hard as well. Also notice that we have a lot of constant values, right? So we have all those flat lines here at the bottom in blue, which is interesting, right? So we'll see how different algorithms take that into account. So that's really it for this little part here. Let's go back into the slides so that we can learn about our very first method. All right, so we are back, and let's take a look at the very first method that we will use here to identify outliers in time series data, which is the mean absolute deviation, or the MAD. So the MAD is fairly intuitive, and I would say this is some kind of a baseline method, okay? So it will work, but not all of the time. You really have to use it in very particular situations, okay? So the idea behind the MAD is that when your data is normally distributed, right, you can reasonably say that points at each tail, at each end of the tails, right, are outliers. Okay, that makes sense. So for example, if you take and this is done by using the z-score method, right? So if your z-score. Here you can see this is basically the point minus the mean divided by the standard deviation. And so this is how you can say, is my point an outlier or not? So usually when your z-score is above like 3 or 3.5, usually we conclude that it is an outlier. So this is basically what we are visualizing here, right? Here you can see this normal distribution, and then on the x-axis you have the z-score. So as you can see here, I set a threshold of 3, so anything above 3 or below -3, you could say that those are outliers. Now, because you have outliers in your data, right, they will affect the mean. And because you are using the mean when computing your z-score, you are affecting the z-score as well, right? So we need to find something more robust, right? Something that will not be impacted by the presence of those outliers. Which brings us to the robust z-score method, that instead of using the mean when computing the z-score, instead we are going to use the median, which we know is a statistic that is much more robust and stable when we have the presence of outliers. So the MAD basically is this formula that you see here. So it is basically the median of xi minus x. Basically, it's the absolute difference between the values of a sample and the median of the sample, okay? And then the way we calculate the z-score is using this following formula. So 0.6745 times the value minus the median of the sample divided by the MAD. And by the way, you might be wondering, why do we need to scale by 0.6745? This is because the z-score uses the median absolute value. It's always smaller than the standard deviation, basically. And so to bring it back to something that looks like a z-score, right? So because you're dividing by a smaller number, your number is going to be like a bit larger. So to bring it back to the scale of a z-score, you multiply by 0.6745, which usually, brings it back to the scale of a z-score. And so you can use it as a z-score method. Now you have to be careful. Okay, so like I said, this is like some kind of a baseline method, very naive, but you have to be careful. The z-score method only works if your data is close to a normal distribution. So first of all, and second, the MAD, if your MAD is not equal to 0, right? So of course, if you're dividing by 0, it's going to be very bad, right? So, and that happens usually when more than 50% of the data has the same value, okay? So if that is the case, usually you cannot use the MAD in that situation. Now, of course, you might remember, right, our data has a lot of constant values, right, a lot of flat lines. And so here in this case, implementing the MAD is definitely not the best of ideas. So I am expecting this not to work very well, but we're still going to implement it just so that you know how to do it if you ever encounter that kind of situation. So that's it for this. Now let's go back into the code and implement this robust z-score method. Okay, and we are back into the code, so I'm just resuming the same notebook that we have started before. And now let's actually implement our kind of a baseline method here, which is the median absolute deviation, or the MAD. And so for that, as you remember, the MAD can be used in two situations, right? When your data is close to a normal distribution and when your MAD is not equal to 0, meaning that more than 50% of your data is actually equal to the median. So for that, we need to take a look at the distribution of our data, see if it makes sense in this case. So here again, just plotting the distribution of my data, very standard, and we get the following. So this is very problematic, right? So as you can see here, this horizontal line indicates the median, and then it matches the peak, right? So that means that a lot of the data actually falls right on the median. Okay, so already first red flag. Okay, I don't know if it's actually 50% of the data that falls on the median, but a big proportion of it actually falls on the median. So already the MAD probably is not going to work very well. And also looking at the distribution, right? This is definitely not a normal distribution. It's very skewed to the left. So again, two red flags in this case, right? It's not a normal distribution, and a big portion of the data actually falls right on the median. So I'm really expecting the MAD not to work here very well, but that's okay. I still want to implement it for you guys so that you know how to do it. So if you ever encounter this kind of situation, you'll be able to do it, okay? So with all that in mind, let's actually implement this mean absolute deviation. or like the robust z-score method actually. So actually the median absolute deviation can be imported from SciPy. So this is what I'm doing here. So here the actual MAD, it's median abs deviation. So let's actually compute it here of df value. Perfect. And let's also take a look at the median. So the median is NP median df value. So we are going to need those values, right, later on to compute the robust z-score. And then once this is done, we can actually print them. So why not? Let's print the MAD and let's print the median like so. And then let's actually define our function already to compute this robust z-score. So I'm just going to follow the formula that we saw on the slide. So compute robust z-score, we pass in some value, and this will simply return 0.6745 times x minus the median, and everything divided by the MAD. So this is simply the formula that we saw to compute the robust z-score. So let's go ahead and run this cell, and you should get the following. So as you can see, big problems, right? Our MAD, our median, absolute deviation is equal to 0.002. So it's not exactly zero, right? But it is very close to zero. So what's gonna happen now probably is that because your MAD is so small, basically any point that is slightly off from the median, right? So anything slightly over or slightly under the median will probably gonna get flagged as an outlier because keep in mind, you're dividing by the MAD. And so here you're dividing by 0.002, which is a very small number. So your z-score is gonna be very large, right? And so even setting a threshold to like 3 or 3.5, you know, chances are that your z-score is gonna be so large that, again, any value somewhat off from the median is going to be flagged as a outlier. But still, you know, let's keep moving ahead just so you can know, you know, how to apply this method. So let's actually compute the z-score for all of our samples. So I will say that df z-score is going to be equal to df value, and then we are going to use the apply method here, which is compute robust z-score. Just like so. So let's go ahead and display the head. Now, as you can see, for each of our sample, now we have our z-score. Perfect. And then, depending on the z-score, we can now determine if a value is either an outlier or an inlier, right? So this is what I'm doing here. So as a baseline, you know, everything is going to be an inlier. And then I use a threshold of 3.5. So here, if the z-score is greater or smaller than, so if it's greater than 3.5, you know, it's an outlier. And if it's smaller than minus 3.5, you know, just to make sure that you cover both ends of your distribution, then it will also be an outlier, so -1. So let's run this, perfect. And now we can move on to the evaluation. So how are we going to evaluate our model? Very simple, we'll use the confusion matrix, okay? So, you know, so we can see what were the predictions from the model and see if the right label was assigned to the value. So very simple, you can import the confusion matrix and confusion matrix display from scikit-learn, and then it's just a matter of plotting it. So I will say that CM is equal to confusion matrix, and then you pass it df is anomaly, like so, and then you also pass it the baseline column. Perfect. And the labels in this case is going to be 1 and -1. All right. And then you say that disp cm, so display the confusion matrix, is going to be confusion matrix display, like so. Pass in your confusion matrix, and then again display labels is going to be equal to 1 and -1. All right. And then you can simply say disp cm dot plot, like so, semicolon at the end, and let's go ahead and run this. And you should get the following. So again, let me zoom out just a little bit. And so this is what you get. So definitely, it was pretty bad, right? It is fairly bad. So of course, as you can see, it did correctly label the 2 outliers that we had in our data, right? So this is what you see, this number on the bottom right corner. So this is great, right? The 2 outliers that were actually outliers were identified by this robust z-score method. However, you can also see that a lot of data was flagged as an outlier when in fact it is not, right? So So let me zoom out again, predicted label -1 here, but the true label is equal to 1. So that means that the model incorrectly labeled normal data as an outlier. And so again, this is to be expected, right? We had a lot of flat values here in this case. The MAD was very close to 0. So again, we see actually what is happening, right? Anything that slightly deviated from the median was flagged as an outlier because of this method, okay? But again, it doesn't really make sense to use it here because not a normal distribution, MAD was very close to 0, but now you actually know how to implement this method. So if you ever encounter that kind of situation, right, you know how to implement this baseline method, and who knows, maybe it's going to work better in some other scenarios. But anyway, that's it for the MAD, for the robust z-score method. So let's go back into the slide. We'll learn about the isolation forest, and then we'll come back into the code to implement it in Python. All right, and now let's take a look at the isolation forest algorithm. So no surprise here, this is a tree-based algorithm that is often used for anomaly detection. And basically the algorithm starts by randomly selecting an attribute, and then you randomly selecting a split value between the maximum and minimum values for that attribute. And so the partitioning is done many times until the algorithm has isolated each point in the data set. And so the general idea behind this is that if it needs many partitions to isolate that particular point, then it means that the point is an inlier. However, if you require few partitions to isolate it, then it means that the point is an outlier. And this really makes sense with this picture here. So as you can see, every red line, so a tree, right, it can only make either a horizontal or vertical lines. So every line is a partition here. And so to isolate this blue point here that is with the arrow here, xi, to isolate it, as you can see, it required a lot of partitions, right? So this means that this data, well, is likely to be an inlier. It's a normal point, okay? However, when you take a look at this point here, xj, now in this case, it only required 4 partitions to isolate it, right, completely. So in this case, this point xj is likely to be an outlier because, well, in this case, you know, very few partitions were necessary in order to isolate it completely from the rest. So that is really all there is to it about isolation forest. As you can see, very simple, very intuitive. So let's implement it right now in Python, and then we will come back to take a look at the last method, which is the local outlier factor. Okay, and we are back, and now let's implement the isolation forest algorithm. So very simple, we're going to import in from scikit-learn, and here I would like to do something a little bit different. So instead of looking at all the data and seeing if the model can actually identify if it is an anomaly or not, let's consider the scenario where you have data and then you want to see if a future point or if a new data point is an anomaly or not, right? So this is really when things get interesting, right? You don't want to know if something in the past was necessarily an anomaly, but it would be interesting to know if a new data point coming in, is this one an anomaly or not, okay? So this is what we are doing here. So this is why we are splitting the data like so, in such a way that we have one anomaly point in the training set and then one anomaly in the test set. So here we'll evaluate the model in its capacity to identify this new anomalous point in the test set, okay? So to use those algorithms, you actually need to set a contamination level. So the contamination is really just the number of anomalous points, right, in your training data. So in this case, it's 1 over the length of train. Okay, so this is something that I know, right? I did split the data just so that we have one anomaly in the training set, one anomaly in the test set. So the contamination is simply 1 divided by the entire number of samples in the training set. And then once this is done, we can go ahead and initialize our model. So iso forest is isolation forest, like so. The contamination is going to be equal to contamination. And then here, let's specify a random state. In this case, I will set it to 42. All right. And then xtrain has to be reshaped. So xtrain is going to be equal to train values and then dot values dot reshape -1 so that we can feed it to the model. And then it's just a matter of fitting the model. So isoforest.fit, and then you pass it xtrain. Perfect. So let's run this, and it shouldn't take too long to fit. And I made a little mistake here. The column is not called values, the column is called value. All right, perfect. So now that this mistake is fixed, perfect, everything worked correctly. And now that our model is fit, we can go ahead and make some predictions. So preds is going to be, preds iso forest is going to be equal to iso forest dot predict, and then pass in your test data, which also has to be reshaped. So test value dot values dot reshape, and then here -1, perfect. So let's run this. All right. And now it's just a matter of evaluating the model. Okay, so let's see if our model was able to identify this new anomalous data point in the test set. So confusion matrix, but only for the test set here. So just like before, CM is confusion matrix. Pass in your test is anomaly, and then your predictions. So preds iso forest, like so, and the labels again, 1 and -1, and then this CM is confusion matrix display. All right, CM display labels, also 1 and -1. All right, and then finally we'll say that this CM plot like so. So let's run this here, and I made a little mistake. I forgot my equal. Sorry about that. And you should get the following. So what do we see here? So looking at the confusion matrix, we can see that in fact it didn't manage to identify this new anomaly, right? So here we would expect to have a 1 at the bottom right, but it's not the case. In fact, the model only predicted that everything is an inlier, basically. So for the model, right, in the test set there are no anomalies, when in fact there is only 1. So that's why, you know, predicted label was 1, but the true label is -1. So in this case, Isolation Forest did not manage to find this new outlier in the data. So that's it for this model here. So let's go back into the slide, learn about the local outlier factor, and then we'll come back into the code so that we can implement it in Python. All right, and now let's take a look at the last method that we'll explore today, which is the local outlier factor. So this is an unsupervised method for anomaly detection. And the intuition behind this method is that we will compare the local density of a point to the local densities of its neighbors. And so if the density is smaller for that point, then the point is likely to be isolated, and so it must be an outlier. So that is really the general idea behind this algorithm. Now, this is all based on a metric that is called the reachability distance. So let me do my best to explain to you what is the reachability distance. So let's take a look at this picture here, okay? So here, suppose that we are looking to compute the local outlier factor of point A, and you set the number of neighbors to 3, okay? So in this case, B, C, and D are the 3 closest neighbors to the point A, and point E is too far away, so we're not going to consider it, okay? So what we'll do, okay, is that we draw a circle around point A. So point A is at the middle, is at the center of this circle, so we draw this black circle around, okay? And then the reachability distance is defined by this formula that you see here, okay? So it is the maximum between either the k distance of B, so between A and B, or the distance or the actual distance, sorry, between A and B. Now, the k distance of B, it is simply the distance from point B to its third nearest neighbor. And that's why in this figure, right, I have another blue circle here with the point B at its center to calculate that k distance of B. So what is the distance from B to its third nearest neighbor? So in this case, it would be C is the third nearest neighbor, right? That's why C is on the edge of this circle. So to calculate the reachability distance between A and B, you would take the maximum value either between the distance from B to C or the distance from A to B, okay? And you take the maximum value of that. And then once you have that reachability distance calculated for all k nearest neighbors of A, you can calculate the local reachability density. And that's simply the inverse of the average of all the reachability distances, okay? And so intuitively, what the reachability density tells us is how far do we have to travel to reach a neighboring point, right? And so if the density is large, then the points are closer together and we don't have to travel for long, okay? And then the local outlier factor, it's simply a ratio of the local reachability densities, okay? So if we set k to 3, we will have 3 different ratios, right? And then we would average them, and this allows us to compare the local density of a point to its neighbors. And now, how do we identify, if the LOF is representative of an inlier and an outlier? Well, if it is close to 1 or smaller than 1, then we conclude that it is an inlier. Otherwise, if the LOF is larger than 1, then it is an outlier. But this has some drawbacks, right? What does it mean smaller, larger, right? Is an LOF of 1.1, does that mean it is an inlier or is it an outlier, right? Is it like larger enough than 1 or not really? So it has some drawbacks, right? And it really depends on the data set, right? Sometimes it's going to work very well. Sometimes it's not going to work that well. It also depends, how far away your outliers are from the normal data. So that's it for this method, and this is the last method that we'll take a look at it today. So let's go back into the code and actually implement it. Okay, so last method that we are going to implement in this lesson is the local outlier factor. So again, a model that you can import from scikit-learn. So from sklearn.neighbors, we'll import the local outlier factor. And then very simple, works pretty much the same way as the previous model. So LOF is local outlier factor. Also set the contamination level here. So contamination is contamination. And here we need to set novelty equals to true, because in this case, this is not necessarily anomaly detection. It is technically novelty detection, right? Because we are fitting on some data and then asking the model to predict on new data if we have anomalies or not. So anyway, be careful with this, right? If you want to use the predict method of local outlier factor, you need to set novelty equal to true. So with that being said, now we can fit the model on our training data like so. Perfect. And then again, just make your predictions. So preds LOF is equal to LOF.predict, and then you pass in your test value dot values dot reshape -1 1. All right. And then once you have your predictions, you are going to plot your confusion matrix. So CM is equal to confusion matrix, and then test is anomaly, like so. And then preds coming from the local outlier factor. Labels is again 1 and -1, like so. And then disp CM is equal to the confusion matrix display. Pass in your confusion matrix, and then display labels is also equal to 1 and -1, and then it's just a matter of displaying it. So disp CM dot plot, like so, and you should get the following. So as you can see now, very interesting, because local outlier factor was able to identify this incoming anomaly in the data set. So as you can see, now we have a perfect confusion matrix, right? Everything, so here's 0 and 0 at the top right and bottom left. So this is exactly what you want to see. And everything that was predicted as an inlier is actually an inlier. And this one anomaly was actually labeled correctly. So for this situation, it turns out that local outlier factor was the best model. All right, well, that's it for this lesson. I hope that you enjoyed it and that you learned something new. You can always follow me on LinkedIn, by the way. I will accept your connection. And also, if you want to read the original article, so this video was actually based on a blog article that I wrote, I will also leave the link below in the description. So that's it, guys. I'll see you in the next one.